Good morning or good afternoon, and we start a new chapter or unit today, and this unit is all about exponential functions and logarithms. So logarithms is probably something you haven't done very much with, but exponential functions might have been something you saw a little bit in Algebra 2. So let's review kind of what they are. All right, an exponential function is one where we have the variable in the exponent. That's what makes it different. So again, we see f of x equals a times b to the x, where a and b are actual numbers. They won't be variables. They'll be real numbers in the problem. A can be any real number, positive, negative, whole number, fraction, doesn't really matter, decimal, all those will work, just not zero. If it's zero, then the whole thing kind of goes away. Then b is any positive number, so b has to be positive, and it can't be 1, because anytime you put 1 to an exponent, it's going to stay 1. 1 to the second power is 1, 1 to the third power is 1, 1 to the fourth power is 1. So 1's kind of a special number in that case. So b can be a fraction. It just can't be a negative number, a 0, or a 1. All right? So let's look at what they look like as graphs. Those are called the parent functions. So I'm going to be looking at this one here first. All right, so in that one there, we are looking at b being positive, and just pretending a is 1, so we don't need a. What a do is, a is called an amplifier or an amplitude. What it does is it kind of makes the graph go up or down quicker or slower. That's all it's doing. If it's a positive number bigger than 1, then it's going to make that thing go up faster or down faster. If it's a fraction, it's going to make things go up slower or down slower. So we're not going to worry about that right now. We just want to get used to the general picture. So again, if b is positive and x is positive, then we get this graph growing from left to right. It's going up. This is actually called exponential growth. It's something we're going to definitely do some work with. The one on the right here, where the b is still positive, but the x is now a negative exponent. Things go the opposite direction. They are going down from left to right, and then flattening out at a horizontal asymptote of the x-axis. So all of these have an x-axis horizontal asymptote, and we call this one exponential decay. Now, if you flip that b number, well, b isn't really negative. We're just making a negative 1, so we're putting a negative out front. It doesn't matter what number it is. It could be negative 2x squared, negative 3x squared, or no, sorry, 3 to the x power, not squared. But if that number out front is negative, then it just gets a mirror image over or reflection over the x-axis and flips. It's still considered exponential growth, but again, it's really reversing and going in a negative direction. And the same thing with the second one on the right there in blue, where if I have two negatives, a negative as the a number, like a negative 1, and then this b number, or the x number is also negative, then again, we get this reflection over the x-axis. So we're going to spend most of our time focused on the ones that we've circled here. These are a little more realistic as far as when it comes to real-world problems. We're still going to look at the ones at the bottom on the negatives, but again, in the real world, these are more useful and more realistic. All right, so here's an example of what you're going to be doing today. All right, we're just going to be kind of learning how these work and trying to figure out where the graphs come from by filling in a table. And in the table, all you have to do is plug the numbers in from the left-hand side. So in this first one, we're looking at 3 to the negative third power. And when you do 3 to the negative third power, and I would expect you to be using a calculator for this stuff, you get 0.037. Now, we're not going to be able to graph that very well, so let's just round it to 2 decimal places, or really almost 1, but we'll call it 0.04. So it means we're going to have a dot at negative 3 and then 0.04. I'm going to go ahead and try to graph that, left 3 spaces and up almost nothing. Now we plug a negative 2 in, so 3 to the negative 2 power. And again, this is something you don't really need to fill in the table very much, if at all. I got 0.1 repeating, so negative 2 and then 0.1, which essentially is just a tiny, tiny bit higher than that first dot. And then I plug a negative 1 in, so 3 to the negative 1 power. And that's 0.3 repeating, so at negative 1, I'm at 0.3. You can see I'm getting a little bit higher, but still not very high. Now when I plug in a 0, well, anything to the 0 power makes 1. So at 0, I get 1, and that is a common fact for all of our exponential functions. When you plug a 0 in as the exponent, you always get an answer of 1. Now, if there's, again, something else happening, we can add more numbers and stuff like that into the problem, as we can add things in, and that can get shifted around a little bit. But in the generic formula, they're always going to be that 1 at the y-axis. All right, then if I start plugging in positive numbers, 3 to the first power, that makes 3. So at 1, I'll be up at 3. So at 1 and 3. And then 3 to the second power, well, that equals 9. So at 2 and 9, I'm going to have a dot. So 2 and 9. And then 3 to the third power, well, that makes 27. So at 3, 27. That's no room for that one. But what I'm hoping you can see is the shape of the graph. You can see that we're hovering right above the x-axis. It's an asymptote. And then we're going to, once we get cross to the first quadrant, cross the y-axis, we start skyrocketing upward. You should have seen a lot of graphs that looked like this when this whole COVID thing started up last spring. So it's things like that are exponential. So this has, again, a lot of real-world applications for this particular type of problem. All right, your work looks like this table today. You got 2 of them. Shouldn't be too terribly difficult or lengthy. Good luck.